All right, let's do some more problems. Just tons of problems in this section, which I always kind of like, but who knows? Let's start with 367 in the textbook. So 367 in the textbook says, evaluate the limits with either L'Hopital's rule or previously learned methods. So it doesn't tell us which one to use. It wants the limit as x goes to 3 of x squared minus 9 over x minus 3. We did this one in the lecture as well, but I want to make another point. Direct substitution does not work. If we use direct substitution, we're going to get 0 over 0, an indeterminate form. Now, we could also just factor and cancel. That's how we did it in chapter 2. But we can also use L'Hopital's rule. So if we wanted to, L'Hopital's rule applies. The functions are differentiable around 3, the top function and bottom function, and we have an indeterminate form. Remember that those are the requirements for L'Hopital's rule. So this is going to be the same as the limit as x goes to 3, derivative of the top, divided by the derivative of the bottom. And now we can use direct substitution to get that same limit that we got in the first video of this section of 6. Don't have to factor if you do it this way. 371, similar problem. The limit as x goes to pi of x minus pi over sine of x. Always try direct substitution. Basically every limit problem ever. Pi minus pi, because these are both continuous functions, so direct substitution makes sense. It's going to be 0. Remember the sine of pi is the y-coordinate on the unit circle at pi radians. The y-coordinate on the unit circle there is 0. So indeterminate form, continuous function on the top, continuous function on the bottom. Sorry, differentiable on the top, differentiable on the bottom, which also means continuous, but the differentiable part's the important part. Says we can use L'Hopital's rule here. Derivative of the top. Don't get tricked by the pi. Pi is just a number. So derivative of x is 1. Derivative of pi is 0. Derivative of sine is cosine. And again, what is the cosine of pi? That's the x-coordinate at pi radians on the unit circle, which is -1. Neat. This used to be a much harder limit to evaluate. Look how easy it was with L'Hopital's rule. Nice. Let's keep going. I like math, guys. 381. Same thing, just another problem. Limit as x goes to 1 of the square root of x minus the cubed root of x divided by x minus 1. Well, as x goes to 1, what's happening? The square root of 1 is 1. The cubed root of 1 is 1. 0 over 0. Indeterminate form. Differentiable function at the top. Differentiable function on the bottom. L'Hopital's rule applies. So rewrite these with rational exponents. The limit as x goes to 1. Let's take the derivative. The derivative of the bottom is much easier. It's just 1. Derivative of the top, again, you're going to need to rewrite these x to the 1/2, x to the 1/3. You're going to get 1/2 x to the -1/2 minus 1/3 x to the -2/3 when you subtract 1 using the power rule. And then you can just evaluate this. I'm going to skip a couple steps because this isn't really anything new. We can actually use direct substitution right now. 1 to the -1/2 is 1. 1 to the -2/3 is also 1. We just get 1/2 minus 1/3, which is 3/6 minus 2/6, which is 1/6. And for all of these, I really would recommend checking your answer, looking at the graph. And the reason for that is, one, it's a good way to make sure that you're right. But it's also really good, really cool to be able to see the limits and get practice. Hold on, I want to make sure I wrote this down right. X minus 1. Get practice seeing what's going on. As x approaches 1, what is the y value getting really close to? A sixth. 0.167 is a sixth. If you don't remember that, there it is. 395. The limit as x goes to infinity of this weird thing. I chose this one because it looked kind of nasty. I hope it is. I hope it's a hard problem. I hope it's a weird one. All right, so if we direct substitute infinity, what kind of happens? We have 1 minus 1 over infinity is like 0. Okay, so this is the 1 to infinity indeterminate form. So all the indeterminate forms other than 0 over 0 or infinity over infinity, all the other indeterminate forms, we just use tricks to make it look like one of those first two forms. Specifically, when we have exponentials, we use tricks with natural log. So we're going to rewrite this as the limit. This was that green one that I wrote in yellow in the notes. The limit as x goes to infinity of e raised to the natural log of 1 minus 1 over x to the x. Then we use properties of natural log that says if we have an exponent in the natural log, it can come down in front. So this becomes the limit as x goes to infinity of e to the x times the natural log of 1 minus 1 over x. Using that function composition theorem, because these functions are continuous on their domains, this is just e raised to the limit as x goes to infinity of x times the natural log of 1 minus 1 over x, which is something else. That will be our final answer. But I want to go off to the side and do these steps somewhere else. Let's look at the limit as x goes to infinity of x times the natural log of 1 minus 1 over x. Well, as x is going to infinity, we're going to get infinity times the natural log of 1. The natural log of 1 is 0. And this is where things get tricky. Because if we have the 0 times infinity indeterminate form, I said we have to put one of these in the denominator. You have a 50-50 chance. One of these is going in the denominator. And I said, usually you keep natural log in the numerator because its derivative is nice. But in this case, the derivative of this inside is not super nice because you're going to have to use the chain rule. So let's just try it. And if we mess up, that's fine. We just try the other combination. There's only two choices. So if you choose wrong, you also get the right answer because then you know which one is right. Unless they both look wrong and then you probably made a mistake somewhere else. So let's put the natural log in the top. It's a good rule of thumb and we'll see if it works. Which means we have to put 1 over x in the bottom. Whenever you do this, take a mental pause and say, are these equal? Dividing by 1 over x is the same as multiplying by x. So they are the same. So now we indeed have 0 over 0. Indeterminate form. The top and the bottom are continuous for big X and differentiable for big X. That's the more important part. We can use L'Hopital's rule. I hate the sound of lawnmowers. I have a push mower. One of my favorite things about my push mower, I have a small yard, is it's kind of quieter than a lawnmower. but it's still kind of loud. Anyway, let's take the derivative of the top, derivative of the bottom, and see what happens. So the bottom's not too bad, negative 1 over x squared. It looks messier than before, but let's have a little faith because the natural log is going to go away. The derivative of the natural log, this top is going to be messy. So we're going to have a fraction in the top, right? Because the derivative of natural log of x is 1 over x. So we're going to have the chain rule. It's going to be 1 over everything on the inside. We're going to have a really messy complex fraction. So I'm actually just going to write this in this form, where it's the derivative of the natural log part divided by the derivative of the other part. Right? Fractions are just division. So instead of making a different, really messy fraction bar, let's just write divided by instead. So derivative of natural log is 1 over that inside. 1 over 1 minus 1 over x times, because of the chain rule, the derivative of the inside. What's the derivative of the inside? Positive 1 over x squared. We've been doing a lot of derivatives right now. I'm not going to go off to the side and do it the long way, but you can show your steps. So this doesn't look super nice, but notice that we have a 1 over x squared divided by a negative 1 over x squared. That's going to be really useful. But let's do that on the next page where we have more room. This is the limit as x goes to infinity of 1 over 1 minus 1 over x. Let's leave that alone for now. Times 1 over x squared. Let's leave that alone for now. Change the division to a multiplication and multiply by the reciprocal. That's all division is. It's just multiplying by the reciprocal. So the only thing that changed is this. Because now we have three things multiplied by each other. We're getting our McDonald's colors out. Red and yellow. And really, this just became so much nicer. Look at this. Let's take that negative out. We do have a negative in front. Negative limit as x goes to infinity of 1 over 1 minus 1 over x. Everything else is taken care of. We just need to simplify this. Or technically, you don't have to simplify this. This limit is just 1. It's easier to see if you simplify it, though. Simplify it. Let's multiply by the LCD, x over x. And we're going to get the negative limit as x goes to infinity of x over x minus 1. And again, there's a bunch of ways that you can see that this is also equal to 1. And there's a negative in front, so negative 1. Or you could use the L'Hopital's rule again. Either way, this yellow limit is negative 1. I'm going to bring that all the way back to here. The yellow limit is negative 1, so our answer is 1 over e. Fun fact, this is actually very close to one of the definitions for e. There's a couple limit definitions of e, Euler's number, but we won't talk about that now. We have 1 plus 1 over x raised to the x. Whoa. As x goes to infinity. Wait, was this it? 1 minus 1 over x. Good. I was like, wait. As x goes to infinity, it's approaching about 0.36. What's 1 over e? Oh, okay. Close to 0.36. Neat. 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 Whoa. It is not, I want to say it's been a long day. It's 11:25. It's not been that long. All right. Was that 395? Yeah, we're on 397 now. 2 more. Graph the function with Desmos and estimate the value of the limit And then you use the L'Hopital's rule to find it directly. So basically the backwards of what we've been doing. X sine of 1 over x. X sine of 1 over x. Actually, let me write it on my board first. The limit as x goes to 0 of x sine over x. So graphically, how does this function behave as x gets close to 0? It's kind of hard to see. Let's zoom in. Oh man, it's doing some weird things. Whoa! Remember, we proved this with the squeeze theorem. Remember the squeeze theorem? You can see it visually. Sine is always oscillating. But it's going to be stuck between +1 and -1. So you can see that it really is squeezed between the line y equals x and y equals -x. You can really see the squeeze theorem here. That's again chapter 2. We think the limit's going to be 0, right? As x goes to 0, the y value is getting close to 0. So we think the answer should be 0. Let's evaluate it and see if we get 0. Direct substitution is going to be 0 times the sine of infinity. This is 0 times something. I don't know. This is not. I'm not convinced we can use L'Hopital's rule here. I don't think we can use L'Hopital's rule because we basically have sine of infinity or sine of something. I don't think we can use L'Hopital's rule. It doesn't tell us to use L'Hopital's rule, right? It does tell us to use L'Hopital's rule. You can't use L'Hopital's rule here. You might get the right answer by using L'Hopital's rule, but as we have introduced this theorem, it doesn't apply here. Book, you disappoint me. Use the squeeze theorem. There's a couple problems with this. First off, we would have to look at one-sided limits. We need one-sided limits because 1 over x, as x goes to 0 from the right, goes to infinity. And from the left, it goes to negative infinity. So right off the bat, there's that. And then sine is going to be oscillating there. So that doesn't really apply for L'Hopital's rule. You're going to have to use the squeeze theorem on this one. But that's how you approach this chunk of problems. I need to make a note to myself so that I tell you guys that. Yeah. Use the squeeze theorem on this one. Review your chapter 2 if you'd like. Let's do 403 and then be done. (403) it's the same type of problem. Let's look at the limit as x goes to 0 from the right of the tangent of x to the x. This one, we're definitely going to be using function composition and L'Hopital's rule. Okay, so let's graph this. The tangent of x to the x and see what it looks like is going to happen. Again, functions raised to other functions are really messy. Oh wait, is Desmos really? Oh wait, we're zoomed in. It's the problem probably. Desmos might be unhappy with this function. This is a function, all right, guys. Isn't math just wacky sometimes? Look at that. It starts oscillating so fast that Desmos is like, oh, I'm having a math is cool. Math is cool. As x goes to 0, maybe that's pi over 2 or something. Something like that. About a little over 1.5. Let's do some math. If we try to use direct substitution, we're going to get the tangent of 0 to the 0th power. We have an indeterminate form on the inside. So tangent's continuous almost everywhere. So as long as it's continuous at the inside limit, we can write it like this. The tangent of the limit as x goes to 0 from the right of x to the x, as long as tangent is continuous, if tangent is continuous at this value. And so we don't know whether we can use this yet. Tangent's continuous almost everywhere. It's also discontinuous infinitely many places. It's possible for something to be both. So we're gonna have to find this green limit. And to find this green limit, we're gonna have to use a yellow limit. We're gonna have multiple blocks of things going off on the side. But eventually we're gonna have the tangent of something, which will be our final answer. Our final answer is gonna be right there. So let's go off to the side and look at a green limit. So we need the limit as x goes to 0 from the right of x to the x. Well, if we use direct substitution, this is 0 to the 0, indeterminate form. We have to write this as the limit. We've done this enough. I think I can do this intermediate step. We're going to write this as e to the limit as x goes to 0 from the right of the natural log of x to the x. And now we're going to go off to the side. So again, this is equal to something, which is equal to something else. We're going to go off to the side and evaluate this yellow limit. I need to calm down. I'm teaching. I'm not just having a good time. I need to be teaching. Solemn Jason today. Okay. So what's this yellow limit? Welcome to the end of class. We can simplify it with properties of natural logs. This is x times the natural log of x. This is the 0 times negative infinity, indeterminate form. So I'll have to rewrite this again and use L'Hopital's rule. So this is the limit as x approaches 0 from the right. We usually like natural log on the top, so we'll write this as natural log divided by 1 over x. Notice that these insides of these yellow limits are the same. Dividing by 1 over x is the same as multiplying by x. This is negative infinity over positive infinity, another indeterminate form. The top is differentiable around 0. The bottom is differentiable around 0. We can use L'Hopital's rule. L'Hopital's rule says this is the limit as x approaches 0 from the right of the derivative of the top divided by the derivative of the bottom. Now we can simplify this and evaluate. This is the limit as x goes to 0 from the right of 1 over x. Dividing by a fraction is the same as multiplying by its reciprocal. McDonald's is coming back again. McDonald's did not sponsor this math lecture. Shell, if you will. I think they're also red and yellow, maybe. I don't know. A bunch of stores are. Just negative x. So as x goes to 0, the yellow limit is 0. So let's go back and plug that in. The yellow limit is 0, which turns this green limit into e to the 0, which is 1. So is tangent continuous at this green value? Is tangent continuous at 1? Yeah. Or sorry. Yeah, it is. Tangent's continuous at 1. So this equals, this green thing is 1, so this equals the tangent of 1 using that function composition theorem from chapter 2. What's the tangent of 1? I don't know. Hopefully it's about 1.5. Oh, thank goodness. I was really nervous. I didn't think it was. Huh. I really was expecting it to be like pi over 2. It's close to pi over 2. That's kind of funny. Yep, that's the limit. Tangent of 1, which is we'll write tangent of 1 as our final answer. You could have a decimal approximation as well. Oh, I even had that box. The box is in the wrong place. Cool. Man, isn't math fun? Isn't math cool? What a wacky function. The final video ends with something as beautiful as this. Let me know if you have questions. Good luck with all your finals, the rest of your classes, and with this class. Enjoy the homework and let me know if you have questions.